So hello everyone, this is day 4 of 100 day FPGA series, and today we will be doing multiplexer and implementing it on FPGA. And we will first understand what a multiplexer is and how it basically works, and then I will show you three ways in which you can implement it in Verilog. So you will have three methods of implementing it, really just syntax changes and all. In the last three videos I have shown you entire flow. So in the last three videos you must have been familiar with the Vivado design flow, and I've also shown you a hardware interfacing on FPGA and Arduino, so that that will make you more familiar with the hardware side of things. And today we are just getting into the building blocks of VLSI design, like this multiplexer, encoder, decoder and all those things. These are just building blocks, right? You will use these things when you make larger designs, like when we go into protocols and stuff, when we'll be doing UART and all. These all things will become important, and in some of those larger designs you might even notice, like you might unintentionally write something that will create these smaller building blocks that will obviously use these smaller building blocks in the base, and you can predict what kind of circuit will be generated if you use certain statements, right? And this is one of those videos that is like the foundation of larger designs. Okay, so it's very important, and today let's start this. Let's first understand what a multiplexer is and what it does, right? This is a symbol for multiplexer. It has two selection lines, and we are doing 4x1 mux right now. The simplest mux is 2x1, but I'm taking 4x1 because this will explain things better. So here in the 4x1 mux we have two selection lines and four input lines and one output line. Okay, based on the selection lines, one of these inputs will be passed to the outputs, whatever those inputs are. Okay, so based on the selection lines, so let's make a truth table simple. If I have, for two selection lines we have four possibilities in Boolean algebra, right? We have 0 0 0 1 1 0 and 1 and 1, right? These are the four possibilities using the two lines. It is and if you see the output, when we select line 0 0, that means we are selecting this 0th line. Okay, 0 0 maps to this line, and then this thing will be passed on to the output. Okay, so I0 will be the output. Similarly in 0 1, this thing will be passed here, and all of those things will be ignored. Okay, so I1, and similarly here, right? So as you can see, we are selecting which input to pass on to the output. Okay, and we are just connecting, think of it as like a wire. You have pins over here, and you are connecting wires between the input and output, and depending on the command you connect different wires. Okay, so this is how it works, and based on the number of selection lines, the input lines will increase or decrease, right? So when you have two selection lines, you can only represent four of the different combinations, right? There is no other combination possible. Two selection lines made four combinations. Similarly, when you have three selection lines, you will have 8 combinations, right? 0 0 0 0 0 1, something like 8. In that series you will have 8 combinations. So that is why it is said that for n number of selection lines you have 2 to the power n input lines, right? This is where it is coming from. So this is what a multiplexer does. So now you understand how a multiplexer works. We will go into Verilog and design this in Verilog, right? I'll show you 3 to 4 ways of designing this thing. I've opened the Vivado here, and let's start designing. We'll create a project. Whenever you design something, the first thing that you should keep in mind is the input and output ports. That's where you start, right? So the number of input ports in this 4x1 mux is going to be this 4, and these two selection line as well. These two are also the input, so these two, and there are 6 inputs, and the number of output is 1. Okay, 6 inputs and 1 output. So I'll input it here. So we have declared inputs and outputs here, and now let's see how we design the mux. Okay, the first method that I'm going to show you will involve in extracting the Boolean expression from the truth table, right? Whenever we have a truth table, something like this, we can always extract a Boolean expression out of it, right? Okay, so the Boolean expression for a 4 by 1 mux is this, and you must have read this in digital electronics as well. So here it's very simple and very easy to understand. As you can see, whenever we plug 0 0, these two will become not of 0, so that is 1, and this will become 1. So 1 and 1 is going to give you 1 only. This will evaluate into I naught. Okay, and the rest, all of the combinations will turn into 0, right? So this is the same with everything else. So this expression implements your 4 by 1 mux. Okay, so let's first off we'll write this expression and see whether we are able to generate the 4 by 1 mux or not. So go into Vivado. Here simply write sine. Written the statement, and let's synthesize the code. Synthesis and run synthesis. In fact, even before synthesis, we can just look at the schematic, RTL schematic that will be generated from the Verilog code that we have written. Okay, so I had written 6 inputs. Let's just change that and run it again. Okay, so as you can see, the expression that we had written here, it has made it using logic gates, right? Let's synthesize it and let's see what kind of structure that we are able to get in the FPGA. Okay, so I'll run synthesis. So the RTL analysis shows that whatever you have written, it simply has drawn it on the schematic, right? Okay, so the design has been synthesized, and let's see the schematic now. Okay, so if you see the schematic again, it has used LUTs, right? As I have told you earlier as well, that in FPGA the LUTs perform everything, right? Every functionality is performed using LUTs. So the functionality of a mux is performed using an LUT, and this entire LUT basically simulates a mux, just one LUT, right? So now the next step for implementing it on FPGA is simply adding the constraints file. I'll use 2 selection lines and 4 input lines. So I'll need 6 slide switches. Now we can directly go to generate bit stream, and we'll be able to generate the bit stream here. So the bit stream has been generated. Now we'll put it on the FPGA. Let's turn the board on and open hardware manager. Here just open target and auto connect. I'll program the device, and okay, let's focus on the FPGA now. So these 4 switches in the constraint files, I have put them as I0, I1, I2 and I3, and this is 0, 1, 2, 3, and these 2 switches are basically S0 and S1. Okay, so 0 0, right now it is 0 0, and that means this input is selected. So whatever I do here, it will be transferred to the output, which is this Y. I've set Y as this LED, right? So whatever I do here will be directly connected to here, and whatever I do with other 3 inputs, it will not be reflected. As you can see, I'm changing it, but the LED is not doing nothing, right? Now if I select 0 1, I'll do 0 1 in the selection lines, and now if I change I0, nothing will happen, but if I change I1, the LED will glow, right? So I1 is equal to Y in this case, right? And any other thing will not take effect. Similarly 0 1 0, basically we'll select this line and nothing else, and 1 1 will select the I3 line. Okay, and it will connect directly the I3 to Y. So this is the application of a multiplexer. As you can see, none of the other ones are responsive. So here you saw the working of multiplexer, 4x1 multiplexer. So you saw the working of 4x1 multiplexer on the FPGA. So now I will describe the other two methods to create a mux, to design a mux. So let's go into the Verilog. I want to bring an attention here. Here I have written expression, right? So this is data flow. If you don't know about data flow, behavioral and structural Verilog concepts, so basically I'll make a video about that as well. I'll make entire one shot of Verilog where I'll explain the basics that is required to get you started into doing FPGAs and get you started into designing hardware. Like, you do not need to learn the entire Verilog first and then move on to hardware. You can start making projects with basic Verilog, right? You do not need to entirely remember all those syntaxes. In fact, I find them useless because learning syntax will not get you much, right? Using them will basically develop your concepts, and the real talent here is basically designing, to be able to design the hardware, not to remember syntax, right? So what I can do, I can write a behavioral statement. How do we write that? We use an always block, right? Whenever we do behavioral design, we write always blocks, right? So here write always at the rate. Now here, since this is a combinational design, the sensitivity list I'll keep to everything, and this means we are basically designing a combinational logic. When we will design sequential logic, we'll put the clock here, right? Positive edge, negative edge, all those clocks here. So here I'm designing combinational logic, so the always block basically is triggered by every input, so I just put star. So inside the always block, I can describe the behavior of the hardware. What is the behavior of the hardware here? If S0 equals 0 and S1 is also 0, then what do we do? Then we are telling the hardware that we are telling the synthesis tool to make y is equal to I0, which is the output, right? Similarly, we will define other conditions. So I have defined all the conditions here, and you can see there is an error right here that we are seeing. When we assign into a variable in always block, you need to have that set to reg. Okay, so I'll set it to reg over here. So y needs to be reg and not wire, and this thing will go away. So now here, as you can see, okay, let's remove this end. So here, as you can see, I have not written any expression, right? I have written the behavior of the hardware, right? I have written the behavior, right? If S0 is this, if S1 is this, then do this. If this S1 is this and S0 is this, then do this. I have written the behavior. I have not written the expression. Yet the synthesis tool is so powerful that it will pick up the it will basically make the hardware, it will generate the circuit based on the behavior itself. It doesn't even require the expression right here. And this is the power of hardware designing. This is the power of hardware description languages and synthesis tools that we have got in our hands, right? We can just describe a hardware and it will generate the hardware for us. We do not even need to describe the data paths and everything, right? This also will generate a mux. And there is a third method in software programming as well. When we do not need a lot of if else, we can change the if else's to case statements, right? So here also we have that, so we can, I'll describe that as well. Need to use case statement, and in the case statement I will basically give input whether we are giving 0 0 0 1 1 0 and 1 1, right? Based on that, a case will be selected, like just like in the C or C++ or Java or Python, whatever you use. Here we need to give it. So first we need to give a concatenation operator for S0 and S1, because we are basically in the case statements we will write 0 0 0 1 1 0 and 1 1, and S0 is 1 bit and S1 is 1 bit, so we need to combine them, right? For combining in Verilog we use this curly braces over here, and I will write S1, the MSB first, and S0, right? So this is combined. Okay, so case, I'll do this and go in here and I will write the first case. Okay, the first case will be when the S1 and S0 are 0 0, and I will just write, this is all syntax you can see, and when these are 0 0, I'll do y is equal to I0, right? Similarly, okay, so at the end we write end case, and now is this thing basically replaces the if else thing that we were writing, if else if else if else if, it basically replaces it. And one thing you also can add here is a default case. Like in software as well, you have a default case, right? In switch case statements. So here I can write a default case where I will basically, if all of those conditions are not satisfied, then this will be satisfied. Okay, so you can generate mux using this as well, right? And in higher designs, like in more complicated designs, you might use these case statements, you might use these if else statements, right? Right now we are just generating mux, so that's why we are just like directly giving the expression, right? In higher designs, these structures like the case structure and if else, all those things will generate multiplexer. In fact, I have a short where I explain how if else is basically implemented in hardware using multiplexer, so you can watch that as well. Now I'll let you verify this on your own. Basically I can verify it here, but I really want you guys to follow along, so please verify these two methods as well. Okay, generate the hardware and test it on the FPGA and tell me in the comments whether you were able to do it or not. Okay.